We will finish today's lecture and our course by looking at an example of interpretation of both carbon and proton NMR spectrum. So imagine we have an unknown compound with the following proton NMR spectrum. Which has 4 peaks, one at 3.5, 2.8, 1.4, and 0.9 ppm. This one integrating for 6 hydrogens, this one for 4, 2, and 4. And this is complemented by the carbon-13 spectrum, which has 4 peaks at 70, 40, 23, and 9. Okay? And the question is, what is the structure of this compound if we know that its molecular formula is C6H16O2? If we're given a molecular formula, then it will always be a good point to determine the number of degrees of unsaturation. So index of hydrogen deficiency, in this case, will be 0 because the saturated hydrocarbon is C7H16, and adding oxygens doesn't change anything, which means that we shouldn't count on any double bonds, rings, or triple bonds in our molecule. Now looking back to this structure, we see 6 hydrogens here, and this will very likely be collection of 2 methyl groups. Now if they're really methyl groups, then and if they have neighbors, they should be splitting those neighbors into quartets according to n+1 rule. And indeed we see that, so this is sort of semi-confirmed. These are 2 equivalent methyl groups, and that they're splitting this neighbor into 4. By looking at the neighbor and knowing that splitting is always mutual, we know that this neighbor now is CH2, 2 CH2 groups, because they split our CH3 group into a triplet. And what these 2 pieces of information tell us is that we have an ethyl group in our molecule, and we have 2 of them in the corresponding integrations. They're 4 and 6. Since we have oxygen in our molecule, but we know that we don't have any unsaturation, we have only 2 choices. It can be an ether, or double ether, or a diol, or a combination of ether and diol. Okay? But we'll get back to that. For now, just by knowing we have these 2 ethyl groups, we have 4 carbons accounted for. Okay? Which means that from our molecular structure, there are 3 more carbons left. However, if you look at our carbon spectrum, our ethyl group itself should give rise to 2 peaks, these 2 peaks, because of the low ppm value. And what we see is that there are only 2 peaks left, which means that our 3 carbon element must have an element of symmetry, so that the central and the 2 peripheral carbons, the central carbon is of one kind and 2 peripheral carbons are of the same kind, which means that we must have this element and we must maintain it in a symmetric orientation. So if we look at this carbon 3 element, then the question is, well, what else do we have left? And if we look at these 2 formulas, this is the total of C4H10. So we have these 3 carbons, 6 hydrogens, and 2 oxygens left to arrange. Thinking about this, we basically could think about this as just 2 OH groups and 2 CH2 groups. Okay? And this is just a guess, but we could try to add the remaining elements onto this without disturbing the symmetry. One way would be to put these CH2 groups here. They still wouldn't disturb the symmetry. And then we could attach an ethyl group onto each one of the CH2 groups. This would maintain the symmetry, but this CH2 group would not be a singlet. It would be a triplet because it's a neighborhood of another CH2. Well, that's not what we're seeing, because these 2 CH2 groups, which integrate for 4 total, are a singlet, so they must not have any neighbors. So perhaps we could do something else. We could attach the ethyl groups over here, giving us something like this, and then stick an OH group here and here to give us our final molecule. This would maintain the symmetry. These ethyl groups and these CH2 groups will have no neighbors. Remember, the neighbors on oxygen do not count. And the symmetry would be maintained, and if you go double back and look at the carbon NMR spectrum, we have 1, 2, 3, 4 kinds of carbons. If you look at the proton, we have 1, 2, 3, 4 kinds of protons. Integrations would be the same, splittings would be the same, and even the chemical shifts would be the same. Would be consistent. This 70 and this 3.5 clearly indicate that the CH2 group is immediately next to an oxygen because it's hydrogen. And so we can now with some degree of certainty conclude that this is the structure of a molecule. Let's look at another example. And the question in this case is which technique will allow you to tell the difference between this ether and this ether? If we think about this example and look at the NMR spectrum, proton NMR spectrum, we should expect a large singlet for the T-butyl group and a smaller singlet for our methyl group. Looking at the proton NMR spectrum here, we would expect a septet for this CH. So it will be a very complex peak. Then we have a large doublet for the methyl groups. And then for the ethyl and the ethyl group on this side, we would again have the same feature of quartet and a triplet. But the point is that we will get a much larger spectrum with four with 4 different peaks. So NMR would be a good way to distinguish between these two compounds. How about these two? This is an ether, and this is similar. Oh, sorry, this is the same compound. This is our other point of comparison. NMR would help us here as well. Here we would have 3 peaks, and here we would have 3 peaks as well. However, 3 peaks here would not be in the neighborhood of each other, so they would both be, all 3 of them would be singlets. Here we have 1 singlet here, but this would be again a quartet and a triplet. It consists with the ethyl group pattern, and so again these two would be readily distinguished by proton NMR. How about this system? There are 2 phenols. One could argue that protons in the neighborhood of chlorine and those in the neighborhood of fluorine should absorb different, and that is indeed the case. But this difference is relatively small and not very diagnostic. And so proton NMR will not be very good in telling us this, and carbon NMR might be a little better, but still not conclusive. IR spectroscopy is also not very good in determining the structures of chlorinated systems because we start getting interference with the absorptions of the optics in the IR itself. And so what we in this case have to use is mass spectrometry. Mass spectrometry is used because we're going to, in the case of chlorine, we're going to see this M and M+2 pattern, which is approximately 3:1 ratio, as well as the simple mass of this will be much higher than this. And so these are some of the examples of how we can use all this to put together a picture of a molecule. And with this we'll close today's lecture and the class itself. We have covered quite a lot of ground, starting from the very basics of organic chemistry. We went through several classes of organic compounds and their reactions, and finally finished with methods of identifying compounds and ascertaining whether our reactions proceeded the way we planned them or not. With this, I will finish, and I will thank you all very much for participating.